Hello, welcome back to Math 245. This is all about binomial probability. So this is lesson 44, Wednesday of week 8, and we've been talking about binomial distributions and binomial probabilities and stuff like that. So in this lesson, we are going to learn more about that. And at first, these equations that we are going to go over might seem a little bit overwhelming and scary, but once we do a couple examples, I think that you'll find it not so bad. So in a binomial experiment consisting of n independent trials, remember our trials have to be independent from each other, the probability of success on each trial is given by some p, so this p is our probability that we will get the result that we want. And the probability of failure is given by q, which is the opposite or the complement of p. The probability of exactly k successes is given by n choose k, p to the power of k, q to the power of n minus k. Another way to write this is with our n choose k multiplied out like this. So this is our formula for the probability of exactly k successes when we are dealing with n number of trials. So let's do a couple of examples to see how our numbers fit into this equation. So we have a spinner that is 75% red and 25% green, and it is spun 6 times. What is the probability of getting green exactly 2 times? So we have lots of different stuff going on here. First of all, we spin this 6 times. That is our number of trials. So n is equal to 6. And we want to get green. So green is success, right? This is what we are considering success. And our spinner is 75% red and 25% green. So the probability of getting green is 25%. So our probability here, p, is equal to 0.25. This means that our q is equal to 1 minus 0.25, which is 0.75. So we have our n, our p, and our q. What about k? What is k? Well, we see that we want to get green exactly twice, and in this formula, k represents the number of successes, and we want 2 successes here. We want to spin green exactly twice. So our k is 2. So according to this formula, the probability of getting 2 greens is given by n factorial over k factorial n minus k factorial. Remember, this is how many different ways there are to choose 2 from 6 times p to the power of k times q to the power of n minus k. All right, let's plug our numbers in and see what this looks like. So this is n factorial is 6 factorial over k factorial, that's 2 factorial. N minus k is 6 minus 2, or 4 factorial. P to the power of k, our probability is 0.25. K is 2. Q is 0.75. And n minus k is 4. So let's see if I can cancel out some stuff with my factorials over here. So this is, well, let's just do this off to the side. So 6 factorial divided by 2 factorial, 4 factorial. This is equal to 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 4 times 3 times 2 times 1. So our 4, 3, 2, 1s cancel, and I can cancel this 2 with this 6, and I'll be left with 3. So we get that this is 3 times 5, or 15. So this number here becomes 15, and then I'm left with 0.25 squared times 0.75 to the power of 4. So 0.25 squared is equal to 0 0.0625, and 0.75 to the power of 4 is equal, whoops, that's not an equal sign, is equal to 0.3164. So if I multiply these all together, I get 0.296, which is 29.6%. This is a good sign, right? And this number right here needs to be between 0 and 1 since we're talking about probability. And this, is a reasonable answer, I think. The probability of getting exactly 2 successes is about 30%. So that is this formula in action. Let's do another example. A fair coin is flipped 10 times. What is the probability of getting exactly 5 heads? So our success here is heads, right? Of course, in this case, since heads and tails are equally likely, it doesn't really matter. This would be the same probability of getting exactly 5 tails, but we're going with it. So our n, the number of trials, is 10. We're flipping the coin 10 times. The probability of getting heads is 0.5. The probability, Q. Do you guys hear my dog in the background? Sorry about that. Our Q is 1 minus 0.5, which is also 0.5. So P and Q are the same here because our chances are 50%. And our K, this is the number of successes that we want, is 5. So our formula says that the probability of getting exactly 5 successes is n factorial divided by k factorial n minus k factorial times p to the power of k times q to the power n minus k. Plugging in our numbers, n is 10, so we get 10 factorial over k is 5, and n minus k is also 5. P to the power of k is 0.5 to the power of 5. Q is also 0.5. Whoops, I wrote k there. To the power of 5. And we get 0.5, that's also Q, and n minus k is 5. So let's see what this can simplify to if I do this off to the side, actually. Whoops. So I want to simplify 10 factorial divided by 5 factorial. Writing this out gives me 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. And on the bottom I have 5 times 4 times 3 times 2 times 1. And again. So one of my 5, 4, 3, 2, 1s will cancel. And then I should be able to cancel some other stuff out as well. So I'm going to cancel this 5 times 2 with this 10. And let's see. I'll cancel this 3 with this 9 and we'll be left with 3. And this 4 with this 8 and we'll be left with 2. So I'm left with 3 times 4 times 7 times 6. And this is equal to 504. So I can rewrite this as 504 times 0.5 to the power of 5, 0.5 to the power of 5. And let's see, 0.5 to the power of 5 is equal to 0.03125, and we have that twice. 0.03125. And if I multiply this out, I get 0.492, which is 49.2%. So the chances of me getting heads exactly half of the time is around 50%. Again, this answer makes sense because it's, first of all, between 0 and 1, which we need. And there's a high probability of getting about half heads since this is a fair coin. So this answer does make sense. All right, hopefully you feel better about this formula now. Let me know if you have any questions. Have a good day.